So good morning, my name is Christophe Finot, and in this presentation I will discuss how it is possible to generate a pair of optical pulses from the nonlinear splitting of a super-Gaussian pulse during its propagation in a nonlinear fiber. So this work has been achieved at the Laboratoire Interdisciplinaire Carnot-Bourgogne at the University of Bourgogne-Franche-Comté in Dijon in France. So when you want to generate pulses with picosecond duration, then you will have to face the limits of the current optoelectronic bandwidth, and you will have to use all optical methods. You can use linear methods such as first-order photonics derivation. It can work quite well. But it is also interesting to see what can be done with nonlinear photonics, and there have been several nonlinear schemes that have been demonstrating taking advantage of the current nonlinearity of the fiber. For example, there have been many studies regarding the pulse doublet that can be generated in fiber lasers with sub-picosecond duration, but a repetition rate of only a few tenths of megahertz. There have been also some suggestion of using the modulation instability process in a dispersion oscillating fibers, but it requires very special fibers. In previous works, we have shown that it is possible to benefit from triangular pulses to make pulse copying. Here, the drawback is that it needs an arrangement of several fibers. So if you want to keep an experimental setup that is quite simple, then one possibility is to use the splitting of a bell-shaped pulse during a process of solitonic compression. So to illustrate this, I will consider the numerical evolution of a pulse, of a Gaussian pulse, with a peak power around 1 watt in the most standard fiber that we have. This is the SMF28 fiber, which is anomalous, dispersive at telecommunication wavelength. So the duration of this pulse will be typical of the duration that we'll use for the rest of this presentation. It will be 42 picoseconds. So we will use the nonlinear Schrödinger equation to model the propagation in the fiber. And what we see is that the initial Gaussian waveform strongly reshape, strongly compress, and after this very strong compression, what we obtain, this is a pair of optical pulses. There are, however, some small pedestals that can be detrimental for applications. The two pulses, they are in phase, but one of the drawbacks is that those two pulses are generated after the point of maximum compressions, and it can be a real drawback because at this point of maximum compression, this is where your spectrum is the broadest and your pulse becomes very sensitive to a lot of perturbations such as third-order dispersion or higher order nonlinear perturbations such as Raman, solitons, and frequency shift. So in practice, it is quite difficult to generate a clean pair of identical pulses. So what we wanted to investigate, this is if there are other ways by just playing with the initial condition to have something that is very stable and that is without any pedestal. So to do this, we have chosen to study what happens if we choose as a starting point a rectangular pulse or a super-Gaussian pulse, in other words, a pulse which has a flat top. So this kind of problem has been already investigated theoretically, for example, in the context of the generation of rock wave. Here, this is a work made by Hell and co-workers. This is a nice work that studies a problem that is known as a box problem and which can be handled with advanced mathematical tools. And what we can see is that the ultra-short structures are not generated at the center of the waveform. The ultra-short structure is generated in the edge of the structures. So it can be here some soliton over continuous background or some standard soliton. And what is also nice is that there is an energy that can be built with the field of hydrodynamics. So we have tried to further investigate these problems, and we have confirmed that there are ultra-short structures that appears in the wings of the pulse. But we have also seen that if we reduce the duration of the pulse, we have a way to control the number of structures that are present in the pulse and to have dynamics that is a bit less complex. And what we have also found is that experimentally, optical fiber has an excellent testbed to observe and characterize these dynamics and the nonlinear coherent structures that are generated. So here, those are demonstrations in the temporal domain, but there are also related problems in the spatial domain. For example, the problem of nonlinear Fresnel diffraction. Here, this is an example of the work made by the group of Jason Fleischer, where there are very intense on-short structures that appears in the diffraction of an edge in presence of nonlinearity. Much more recently, similar problem has been investigated by the group of Claudio Conci, which has discussed how to control the number of structures that may appear during the nonlinear propagation. So, in practice, what we have done, this is we have tested a lot of various temporal duration to identify the best duration that we may have to generate clean doublets of pulse. So we have found that for super-Gaussian pulse with a duration around 40 picoseconds, we observed the generation of two pulses without any side lobes of pedestals. Those two pulses, they are in phase. And what is also nice is that this doublet is generated before the point of maximum compression, so that we will not suffer from the drawback that I have mentioned previously. We can compare this result with the result of the evolution of a typical bell-shaped pulse in similar condition, and we clearly see the difference between the two kinds of nonlinear dynamics. We see that we cannot use the dynamics of a bell-shaped pulse to predict what happens when we start with a waveform that is flat top. So now if we look in more details in the intensity profiles, we see that the resulting pulse can be well adjusted by a Gaussian waveform. And the Gaussian waveforms are transform limited. We see here that we have a nice fit between the assumption of a pair of Gaussian-like pulses that are transform limited and the spectrum that is predicted by numerical simulation. One potential limitation, this is this small bump that is here at the center of the doublet. So now here is the experimental setup that we have used. So we start from a continuous wave and we use an intensity modulator driven by an electrical pattern generator operating at 2 GHz. So we are working here in the telecommunication window. What is important, this is that our initial condition is highly symmetric, both in the temporal as well as in the spectral domain, and it will be very important to have a duplex of identical pulses. To observe the nonlinear propagation, we first amplify the pulse train thanks to an ob fiber amplifier. Typically, the average power that I've involved are around 100 milliwatts, which is quite low to observe nonlinear effect. We studied the influence of the average power using an optical variable attenuator, and the nonlinear propagation takes place in 3.6 kilometers of SMF28 fiber. So we have here chosen to use 4 spools of this fiber, because we wanted to insert some optical isolator between each spool. So it slightly increased the level of loss, but the motivation was to avoid the buildup of brilliant backscattering. So with this, we managed to avoid all the deleterious impact of brilliance. At the output, we characterize the resulting pattern using an optical spectrum analyzer, which enable us to get both the intensity and phase profiles of the pulse train. So here this is a complex optical spectrum analyzer. So here are the experimental results, and we see that the trend that we observe, they are very well confirmed by the numerical simulation that take into account also the losses of the fiber. So we have, for a given power, the generation of the expected pulse doublet. And the agreement is also excellent when we have a look at the spectrum. So now, if we look more in details to the profile, the temporal profiles of the pulse that are generated, once again we see an excellent agreement with numerical simulation. I would say perfect agreement, and we see also that initially the small bump that was predicted with simulation without losses does not appear when we take the losses into account. So here there is a benefit of having some propagation losses. In more details, the pulses are spaced by 15 picoseconds. The two pulses are in phase. The duration is around 4 picoseconds, which represent a compression factor around 10. And if we have a look at the intensity profile obtained for other level of initial power, what we can see is that we can adjust the output pulse shape by 3 or 2 Gaussian waveforms. It works quite well. Well, here this is not a demonstration. This is not a theoretical demonstration, just an experimental fit. So to conclude, we have investigated the nonlinear dynamics experience by a super-Gaussian in a nonlinear fiber, and we have shown that it is very different from the dynamics of a bell-shaped pulse. We have been able to demonstrate that an initial super-Gaussian pulse can split into 2 Gaussian-like pulses that are in phase, and this splitting occurs before the point of maximum compressions. And what is nice is that this nonlinear reshaping requires only a single fiber with anomalous dispersions and very moderate powers, and there is no restriction regarding the repetition rate. So if you want to have more details on this work, you can read this publication. Thank you for your attention.